Number 25. The Antarctic Snow Cruiser. Built in 1939, this 55-foot diesel-electric laboratory had living quarters, scientific equipment, 10-foot tires, and space for a small airplane on its roof. Then it reached Antarctica. The smooth tires sank and spun. The crew discovered that the machine moved better backward, and its longest journey, 92 miles, was completed in reverse. It eventually became a stationary scientific base. The abandoned cruiser was found beneath the snow in 1958, but its later fate remains unknown. Movement and breakup of the surrounding ice may have carried it into the ocean. The machine did not fail because Antarctica was too cold. It failed because it could not grip the surface it had been built to cross. Number 24. The Armstead Snow Motor. The Armstead system replaced wheels with two counter-rotating cylinders wrapped in spiral blades. A surviving 1924 demonstration film shows versions fitted to a Fordson tractor and a Chevrolet automobile. As the cylinders rotated, their helical blades pushed against snow and dragged the vehicle forward. In deep, soft terrain, the system could travel where conventional wheels sank. On hard ground, the advantage disappeared. The metal screws were inefficient, difficult to steer precisely, and poorly suited to roads. It was not a better wheel, it was an answer to one surface, and a problem almost everywhere else. Number 23. The ZIL-2906. Soviet spacecraft did not always land near roads. The ZIL-2906 was developed to help recovery teams reach Soyuz capsules in deep snow, swamps, water, and other terrain that stopped conventional vehicles. Two counter-rotating screw-shaped pontoons provided both flotation and propulsion. A larger recovery truck transported the machine until ordinary wheels could go no farther. Then the screw vehicle took over. It was slow and damaging on firm ground. But firm ground was not its mission. Its mission began exactly where normal transportation ended. Number 22. The Tourneau C-22 Snow Freighter. This roadless freight train used diesel generators to supply electric motors in all 24 wheels. Behind the control unit were 5 cargo sections, each rated for roughly 25 tons. Together, they could carry approximately 125 tons across Arctic terrain without rails or a prepared highway. Its enormous length distributed the load, but it also made the vehicle difficult to maneuver. During its Alaskan service, the snow freighter suffered a jackknifing accident, followed by an engine fire. The one-off machine never returned to regular operation. It solved the cargo problem. It did not solve the recovery problem. Number 21. The Rotary Snowplow. A rotary snowplow uses a giant powered cutting wheel to break into deep snow and throw it away from the railway while locomotives push from behind. The design appeared in the late 19th century and could defeat drifts that stopped ordinary wedge plows. But a rotary was slow, expensive, fuel-hungry, and required specialist crews. Railroads increasingly focused on clearing snow before it became deep enough to require one. Rotary plows did not disappear because they failed. They became rare because prevention was cheaper. Some remain available for the moments when prevention fails. Snow rewards machines that spread their weight. Railways demand the opposite. Every vehicle must follow one exact path. So engineers try to make trains balance on a single rail, hang above the ground, and even move like aircraft while still trapped on tracks. Number 20. The Lartigue Monorail. Ireland's Listowel and Ballybunion Railway opened in 1888. Its vehicles straddled a raised central rail supported by A-shaped frames. 2 lower guide rails prevented the trains from tipping. The system reduced the amount of heavy running rail, but every load had to be balanced between both sides. Crossings, switches, passenger cars, locomotives, and freight equipment all required special designs. The line accumulated financial problems, and damage associated with the Irish Civil War made its condition worse. It closed in 1924. The train itself worked. The isolated transportation system around it did not work well enough. Number 19. The Brennan Gyroscopic Monorail. Louis Brennan's full-size prototype balanced on one conventional rail using 2 rapidly spinning gyroscopes. Demonstrated in 1909, the vehicle was about 40 feet long, weighed approximately 22 tons, and could carry an additional 15 tons. The demonstrations proved that active gyroscopic stabilization could keep a heavy vehicle upright. They also exposed the central trade-off. 2 ordinary rails provide passive stability. Brennan's vehicle required powered, precisely controlled machinery to reproduce the same result on one. It was a brilliant solution. The advantage did not justify the machinery needed to create it. Number 18. The Schienenzeppelin. In 1931, this German propeller-driven railcar reached 230.2 kilometers per hour, about 143 miles per hour. The streamlined body and rear-mounted aircraft propeller produced extraordinary speed for the period. They also produced a problem no station could ignore. An exposed propeller was dangerous near passengers, railway workers, platforms, and enclosed stations. The layout also made it difficult to attach ordinary passenger cars. The prototype proved that rail vehicles could travel dramatically faster. It did not prove that an airplane propeller belonged inside a railway station. The Schienenzeppelin was dismantled in 1939 as high-speed rail development moved toward more practical propulsion systems. Number 17. The Beni railplane. George Beni wanted fast passenger traffic to move above slow freight trains. His railplane hung beneath an overhead rail, used lower guide rails for stability, and was driven by propellers at both ends. A 130-yard demonstration line opened near Glasgow in 1930. The vehicle operated successfully, but every commercial route would have required an entirely new elevated structure. Beni failed to secure enough investment and was bankrupt by 1937. The unusual passenger cabin was not the expensive part. The real machine was the railway that had to be constructed everywhere above it. Number 16. The French Aerotrain. The Aerotrain floated on a cushion of air above a concrete guideway. Different prototypes used propellers, gas turbines, or linear motors. In 1974, the I-80HV reached 430.4 kilometers per hour, 267.4 miles per hour. The speed was real. So was the infrastructure problem. A commercial Aerotrain system required its own dedicated guideway. The competing TGV could use conventional steel rails and connect with existing stations and railway networks. The French government canceled the planned commercial Aerotrain line in 1974 as national support shifted toward the TGV. Compatibility defeated raw performance. Water removes the rails. Then it adds waves, drag, corrosion, and instability. That is how ships end up shaped like coins, office buildings, insects, and aircraft that never travel far from the surface. Number 15. Novgorod. Launched in 1873, the Russian monitor Novgorod was approximately 101 feet long and almost exactly as wide. Its circular hull supported heavy armor and two 11-inch guns, while drawing only around 13 feet of water. It was designed as a shallow water coastal defense platform, not as a fast ocean cruiser. Its maximum speed was only around 6.5 knots, and its steering performance was limited. The circular shape looks absurd, only if speed is assumed to be the priority. For Novgorod, heavy weapons, armor, and shallow draft mattered more than traveling efficiently. Number 14. Flip. Flip was a 355-foot oceanographic research platform that traveled horizontally and then rotated 90 degrees at its worksite. Seawater flooded ballast tanks in its long stern. Most of the structure descended vertically until approximately 300 feet extended beneath the surface. That placed most of the platform below ordinary wave motion, producing an exceptionally stable base for acoustic, oceanographic, and atmospheric research. Flip was retired in 2023 because extending its operational life had become too expensive. But its story did not end there. In 2024, the marine technology company Deep intervened before the platform was scrapped and announced plans to restore and modernize it. Its strange geometry still solved the problem well enough to earn another life. Number 13. Sea Shadow. Lockheed's Sea Shadow looked like a dark office building resting on two narrow hulls. The experimental vessel was constructed for the United States Navy to investigate stealth at sea. Its sloped surfaces reduced radar reflections, while its submerged twin hull configuration improved stability in waves. Sea Shadow was not an unfinished battleship waiting for weapons. It was a floating laboratory for low observable shapes, automation, sensors, and naval architecture. Once its testing role ended, maintaining the unique vessel offered little additional value. It was eventually dismantled. The platform disappeared. The information gathered from it did not. Number 12. Proteus. The 100-foot Proteus introduced the wave adaptive modular vessel concept at full scale in 2007. Articulated structures connected its central cabin to separate outrigger hulls, allowing different parts of the vessel to respond independently to wave motion. Instead of forcing the entire craft to behave as one rigid object, the design adapted its geometry to the surface beneath it. The large Proteus remained primarily a technology demonstrator, but the underlying WAM-V architecture survived. Smaller unmanned versions are used as modular platforms for ocean research, surveying, sensing, and autonomous navigation. Proteus did not become the universal ship of the future. It became an oversized ancestor. Number 10. Bagger 288. Bagger 288 weighs approximately 13,500 metric tons. Its rotating bucket wheel continuously cuts into overburden and transfers the material onto conveyor belts running through the machine. Under suitable conditions, it can move up to 240,000 cubic meters in a single day. Despite its size, it travels at only around 2 to 10 meters per minute. Wide tracks distribute its weight, but relocating it requires requires prepared ground, electrical power, and careful planning. This is not simply a giant excavator, it is one moving component inside a production system the size of a landscape. Number 9. Big Muskie. Big Muskie was the largest walking dragline ever constructed. It weighed approximately 13,500 short tons and carried a bucket with a capacity of 220 cubic yards. The empty bucket alone weighed roughly 230 to 240 short tons. Fully loaded, it could contain as much as 325 short tons of material. Instead of conventional tracks, hydraulic walking feet shifted the machine a short distance at a time. Big Muskie stopped mining in 1991 and was dismantled in 1999. Its bucket remains on display in Ohio. Number 8. The F6O Conveyor Bridge. An F6O overburden conveyor bridge stretches 502 meters, more than 1,600 feet. It carries excavated material across an open pit mine instead of forcing trucks to drive around the excavation. Its running gear includes 760 wheels, approximately half of them powered. 5 F6O bridges were constructed for East German lignite mining. The unit preserved at Lichterfeld operated only from 1991 until 1992 before the mine closed. Number 7. The Captain. The Marion 6360 stripping shovel, nicknamed the Captain, weighed approximately 12,700 metric tons. Its 180 cubic yard bucket removed the layers of earth covering coal deposits. In September 1991, a hydraulic line failure contributed to a major fire in the lower section of the machine. The damage was judged uneconomical to repair, and the Captain was dismantled the following year. Number 6. The raise boring machine. A raise boring operation begins by drilling a relatively small pilot hole from an upper level to a lower underground tunnel. Workers attach a much larger reaming head at the bottom. The machine then pulls that cutting head upward, enlarging the opening as broken rock falls to the lower level. The method creates ventilation shafts, ore passes, and access openings without placing workers directly beneath conventional drilling and blasting operations. Unlike many machines on this list, raise boring equipment did not disappear. It became standard because gravity removes the debris for free. Number 5. The BV206. The Swedish BV206 consists of 2 tracked bodies connected by an articulated steering unit. Power is delivered to the tracks on both sections, while the flexible joint allows them to remain in contact with uneven ground. Its low ground pressure lets it cross snow, mud, marshland, and other surfaces where heavier vehicles sink. Many versions can also travel through water. The basic principle survives in newer articulated vehicles such as the BVS-10 and Beowulf, which have been proposed or used for military transport, emergency response, and rescue work. It looks broken in the middle. That is exactly where its mobility comes from. Number 4. NASA's M113 rescue vehicle. During the space shuttle era, armored M113 personnel carriers waited near the launch pad. Astronauts could use one to evacuate after escaping from the launch structure. Firefighters and rescue personnel could use another to approach through heat, debris, smoke, or hazardous propellants. Shuttle crews received training in how to drive the vehicles themselves. Later spaceflight programs moved toward newer mine-resistant emergency vehicles. For decades, however, one of humanity's most advanced spacecraft depended on an evacuation machine, valued not for speed or sophistication, but for being a bunker that could move. Number 3. The Wheelbarrow Bomb Disposal Robot. The British Army developed the original wheelbarrow during the early 1970s. Initial versions were crude remote-controlled platforms carrying cameras, tools, and equipment for handling suspected explosives. They did not need speed, elegance, or sophisticated autonomy. Their purpose was to let a machine approach the bomb first. Wheelbarrow variants remained in service for decades. Newer T-7 robots began replacing them around 2019 and 2020, offering improved mobility, sensors, manipulators, and control systems. The technology changed. The logic did not. A bomb disposal robot can be destroyed and still complete its most important task, keeping its operator somewhere else. Number 2. The Fenix 2 capsule. The 33 Chilean miners rescued in 2010 were trapped roughly 2,300 feet underground. Fenix 2 traveled through a rescue shaft approximately 623 meters long, just over 2,000 feet to reach them. The capsule was only about 21 inches wide. Inside that diameter, engineers fitted retractable guide wheels, oxygen equipment, lighting, communications, safety restraints, and an emergency escape hatch. Each journey carried one miner through hundreds of meters of solid rock. After 69 days underground, all 33 reached the surface alive. The capsule's dimensions were dictated not by comfort, but by the hole engineers had managed to drill. Number 1. Big Wind. In 1991, Hungarian firefighters brought Big Wind to Kuwait. The original machine combined a tracked T-34-based chassis with 2 turbojet engines from MiG-21 fighter aircraft. Water was injected into the jet exhaust, producing a high-speed stream of gas and mist. The blast pushed flame and oxygen away from the erupting oil while the water absorbed heat. Big Wind extinguished 9 burning wells in 43 days. The machine was later rebuilt on a more modern T-55-based chassis, but the principle remained unchanged. When a fire behaves like a storm, fight it with an artificial hurricane. These machines looked wrong because each one obeyed a constraint more important than looking normal. Some of these machines failed. Some were too expensive, too specialized, or tied to a world that disappeared around them. But others survived in a different form, in articulated rescue vehicles, wave-adaptive vessels, raise-boring equipment, bomb disposal robots, and machines built for places ordinary engineering still cannot reach. A machine starts looking wrong when the problem it was designed to solve is no longer visible. Once the problem is visible, the shape stops being absurd. It becomes the answer.